So, I want you to imagine that you are building something enormous.
Hmm.
Let's say you're building a massive house, right?
Okay, a huge house, got it.
Yeah, and you spend months on it. You do the foundation, the framing, the roof. But when the house is finally finished, you look around the yard and it is just completely littered with offcuts.
Right, like leftover bricks, bent nails deep in the grass, that kind of thing.
Exactly. Piles of sawdust, bits of timber that were just, a little too small to actually use in the framework. Well, when you look up at the night sky, our solar system is actually a lot like that cluttered yard.
It really is. I mean, about 4.5 billion years ago, you had this vast, chaotic cloud of gas and dust, and it collapsed, swirled into a giant disk, and the center ignited into our sun.
And the rest of the material kind of clumped together to form the planets.
Right. But just like building that house, not absolutely everything got used. There were billions of leftover scraps that were just, never gathered up into a finished world.
Which brings us to the mission of our deep dive today. We are going to explore these ancient planetary offcuts. We always talk about the big finished products, the planets, the moons, the sun.
But to truly understand the environment you live in, you have to look at the leftovers. Those drifting ancient time capsules that have basically been sitting in the deep freeze of space since the dawn of the solar system.
Because they hold the original blueprints, right, like the untouched materials. So we're going to untangle the differences between them, debunk some massive Hollywood myths, look at the existential threats they pose, and spoiler alert, how they might be responsible for our very existence.
It's a wild story, and the best place to start is with the offcuts closest to home, the rocky ones, which we generally call asteroids.
Right. So asteroids are essentially chunks of rock or metal. They vary wildly in size from a tiny pebble to a behemoth hundreds of kilometers across. And most of them hang out in the main asteroid belt, which is that wide zone between Mars and Jupiter.
They do.
Mm.
And their composition actually tells us a lot about the early solar system's temperature. They formed closer to the sun inside what we call the frost line.
The frost line, so it's too hot for ice.
Exactly. It was simply too hot for volatile compounds like water or methane to remain solid. So the only things that could condense and survive the heat were heavy, refractory materials, basically, metals and silicates. That's why asteroids are rocky.
Okay, that makes sense. Now, before we go any further, I have to tackle the Hollywood myth of the asteroid belt because, honestly, it drives me completely crazy.
Oh, I know exactly what you're going to say.
Right, because in basically every sci-fi movie, a spaceship flies into an asteroid field, alarms are blaring, the pilot is sweating, and they're frantically weaving through this dense field of tumbling boulders that are constantly smashing into each other. That is a massive exaggeration, isn't it?
It is an entire cinematic invention. Space is, above all things, unfathomably roomy.
Roomy, I like that.
Yeah, I mean, while there are millions of asteroids in the main belt, they are spread across such a staggering volume of space that the belt is practically empty. To give you a sense of scale, if you took every single asteroid in the main belt, right,
Uh-huh.
and you crushed them all together into one single object, that object would still be smaller than our moon.
Wait, really? The entire asteroid belt combined is smaller than the moon.
Considerably smaller. It's actually only about 4% of the moon's mass.
That is mind-blowing.
So if you were standing on the surface of an asteroid in the main belt, you very likely wouldn't even be able to see the next nearest asteroid without a high-powered telescope.
Wow.
The average distance between them is hundreds of thousands of kilometers. You would just be standing there completely alone in the dark.
Okay, well, that completely reframes the picture for me, but it also brings up a pretty strange contradiction, I think.
How so?
Well, if there's enough material out there to form something, even if it's smaller than the moon, why didn't it clump together over 4 billion years? Like, why is it just millions of scattered shards instead of a dwarf planet?
Yeah, that's where the unseen architectural force of the solar system comes in gravity. And in this case, the architect was Jupiter.
The gas giant.
Yeah, Jupiter is an absolute monster. As it orbits the sun, its immense gravitational pull acts almost like a whisk. It creates these things called orbital resonances.
Orbital resonances, so it's like a rhythm.
Exactly. Jupiter's gravity periodically lines up with the orbits of these rocks, giving them a regular, repeating gravitational kick.
Oh, I see. So if the asteroid belt is a bunch of wet cement and bricks trying to set, Jupiter is like a giant restless dog constantly running through it, kicking up the materials and making sure it never actually solidifies.
That is a great analogy. It captures the disruption perfectly.
Yeah.
To form a planet by accretion, you need a relatively calm environment.
Right, where things just sort of gently drift together.
Exactly. Where dust and rocks can gently bump into each other and stick, gradually building up mass and gravity. But Jupiter's resonant kicks accelerated those rocky chunks to super high velocities.
So they were moving too fast to stick.
Much too fast. When they intersected, they weren't gently bumping. They were slamming into each other at thousands of miles an hour. They shattered instead of clumping. Jupiter effectively weaponized the asteroids against each other.
It just bullied them into staying shattered. Okay, so Jupiter's gravity kept the rocky scraps near us from forming a cohesive world. But what about the scraps that were pushed way, way out, like far past Jupiter, into the freezing dark edges of the solar system?
Well, that isolated freezing environment is what gives us comets. Because they form so far from the sun, well beyond that frost line we just talked about, materials like water, ammonia, and methane could freeze completely solid.
I've heard them called dirty snowballs.
Yeah, astronomers use that term a lot, and it's a fairly accurate description of a comet's core. It's a messy amalgamation of ice, frozen gases, dust, and dark rock.
And their isolation is just staggering. I know they hang out in two main reservoirs. You've got the Kuiper Belt, which is a thick wing of icy bodies just beyond Neptune. But then there's the Oort cloud, which is almost hard to even comprehend.
The Oort cloud really requires a massive leap in how we visualize our solar system. It isn't a flat ring like the asteroid belt or the Kuiper belt. It is a vast, spherical shell of icy debris that completely encapsulates the entire solar system.
Like a giant bubble.
Right, and it extends so far out into interstellar space that its outer edge reaches almost halfway to the nearest star.
That's insane.
It is. A single comet originating from the outer Oort cloud might take millions of years to complete just one agonizingly slow orbit around the sun.
Millions of years for one single lap, just drifting in the absolute deep freeze. But, here's where it gets dynamic. Out there, a comet is basically a dark, invisible lump of ice doing absolutely nothing. But occasionally, a gravitational nudge sends one of these frozen lumps falling inward, right toward the inner solar system. And when it gets close to the sun, it puts on a massive show.
This is where we see the transition from a dormant snowball to an active comet. As it crosses the orbit of Mars and approaches the sun, solar radiation rapidly heats the comet's surface.
But wait, in the vacuum of space, liquid water can't exist, right? So it can't just melt.
Exactly. The ice doesn't melt, it sublimates. It flashes directly from a solid ice into a gas.
Just like dry ice at a Halloween party.
Precisely like dry ice. And this violent transition releases this massive, expanding cloud of gas and dust that totally shrouds the tiny solid core.
Yeah.
We call that glowing, fuzzy envelope the coma.
The coma. And streaming off of that, of course, is the famous comet tail. Now, I want to pause here for a second because the physics of that tail completely brought on my brain when I first learned about it.
It's very counterintuitive.
It really is, because a comet's tail does not behave like a trail of smoke behind a speeding train.
No, it doesn't. And that's because our intuition is entirely based on atmospheric drag. On Earth, if you run with a sparkler, the smoke and sparks trail behind you because you're pushing through air, and the air pushes the smoke back.
Right. But space is a vacuum.
Exactly. There is no air resistance to drag the tail behind the comet. Instead, the tail is entirely dictated by the sun. And to be precise, a comet usually has two distinct tails.
Two tails.
Yes. As the ice sublimates and releases dust and gas, those two materials actually react differently. The heady dust particles form a glowing, slightly curved tail that is physically pushed outward by the radiation pressure of sunlight itself.
Wait, sunlight actually exerts pressure.
It does. Photons from the sun are literally pushing the dust away. But then there is the gas, which gets ionized by the sun's ultraviolet light. This creates an ion tail, which gets caught in the solar wind.
And the solar wind is what, like a stream of particles?
Yeah, charged particles constantly blowing out from the sun in all directions. So that ion tail shoots straight out, directly away from the sun, like a windsock in a hurricane.
Okay, wait. So if both the dust tail and the ion tail are always being blown away from the sun, that means when the comet hits its closest point, swings around the sun, and starts heading back out into deep space, the tail is actually leading the way.
Yes. Visually it is.
It's flying through space looking like it's going backwards.
It's a bizarre visual, isn't it? As the comet retreats back toward the Kuiper Belt, the solar wind is still blowing from the center of the solar system outward, so it is constantly pushing that coma material ahead of the comet's rocky core.
That is just incredible. It perfectly illustrates how solar radiation totally overrides the comet's own momentum. But as beautiful as these mechanisms are, we do have to talk about the darker side of this debris field.
Ah, yes, the impacts.
Right, because as long as these rocky and icy offcuts stay in their distant belts and clouds, they're just beautiful curiosities. But the story turns incredibly dramatic when one of those orbits crosses the path of a planet.
And we know with absolute certainty that Earth's path has been crossed many times. The most famous one, of course, occurred 66 million years ago.
R.I.P. the dinosaurs.
Exactly. It ended the 150 million year reign of the non-avian dinosaurs. A rocky asteroid, roughly 10 kilometers across, struck the shallow sea in what is now the Yucatan Peninsula in Mexico.
Okay, I have to push back on the scale here for a minute because I think it's something people really struggle to visualize.
Sure.
A 10-kilometer rock is like the size of a small city. To a person, that is massive. But compared to the Earth, which is over 12,000 kilometers in diameter, a 10-kilometer rock is quite literally a speck of dust on a bowling ball.
That's a fair comparison.
So how does a single localized impact from a speck manage to darken the skies of the entire planet and trigger a mass extinction? It just seems mathematically disproportionate.
It does seem disproportionate until you factor in kinetic energy. The destructiveness of an impact isn't just about the mass of the object, it's heavily dependent on velocity. The equation for kinetic energy squares the velocity.
Oh, wow. So speed is the real killer.
Exactly. And this asteroid was likely traveling at over 70,000 kilometers per hour. Yeah. When it slammed into the Earth's crust and halted in a fraction of a second, all of that orbital momentum was instantly converted into heat and shock waves.
So it's not a physical puncture at all. It's a colossal explosion.
A massive one. The energy released was roughly equivalent to 10 billion World War II-era atomic bombs detonating simultaneously.
10 billion? I can't even fathom that.
It's unfathomable. But the size and speed were actually only half the problem. The asteroid was also geologically incredibly unlucky in where it hit.
Really? Location mattered that much?
Oh, massively. The bedrock in the Yucatan Peninsula is rich in gypsum and anhydrite, which are minerals packed with sulfur. The immense heat of the impact instantly vaporized the asteroid and billions of tons of this bedrock.
So it blasted all that vaporized rock and sulfur into the sky.
Right. Pulverized rock, soot, and sulfur aerosols were blasted high into the stratosphere and even out into space.
And because it's in the stratosphere, which is above the weather, it doesn't just rain out immediately, right? It spreads globally.
Yes. Those sulfur aerosols enveloped the entire globe, creating a dense haze that reflected incoming sunlight back into space. The Earth's surface was plunged into a sudden, freezing darkness that lasted for years.
And without sunlight, the plants die.
Exactly. Photosynthesis ground to a halt. The base of the food web collapsed, taking the dinosaurs and roughly 75% of all plant and animal species on Earth with it.
And the wild part is, the evidence for this isn't just theoretical modeling. We can literally see the chemical fingerprint today.
We can. Aside from mapping the buried 150-kilometer-wide Chicxulub crater, geologists have found a distinct boundary line in rock formations all over the world, dating to exactly 66 million years ago.
The KT boundary, right?
Yes, the KT boundary. It's a thin layer of clay that is highly enriched in iridium. Now, iridium is an element that is exceedingly rare on Earth's crust, but very abundant in asteroids.
So it's the literal fallout ash of an apocalypse, just preserved in stone all over the globe.
Precisely.
Which obviously instantly raises the most terrifying question for anyone listening. Could this happen to us? Could a city-sized rock be silently hurtling toward us right now?
Well, the physics of the solar system haven't changed, so impacts are a natural part of our environment. But humanity occupies a unique position. Unlike the dinosaurs, we aren't just looking down at the grass, we are actively looking up.
Right, we have transitioned from simply being at the mercy of the cosmos to actively surveying it. Astronomers are constantly running systematic surveys to catalog what they call near-Earth objects, or NEOs.
Exactly. They are continuously mapping the trajectories of these objects and projecting their orbits decades into the future. And the reassuring news is that the truly civilization-ending giants, the 10-kilometer behemoths, are relatively rare.
And they're big enough to spot, right?
Crucially, yes. They are bright enough to be easily spotted. NASA estimates we have found over 90% of the near-Earth objects that size, and none of them are on a collision course for the foreseeable future.
Okay, that is definitely a relief. Though I imagine the smaller ones, the ones that could take out a city rather than a whole species, those are much harder to track.
They are numerous and definitely harder to spot.
But let's say we did spot one. Let's say 20 years from now, astronomers find a sizable rock with Earth's name on it. What do we actually do? I mean, we aren't calling Bruce Willis to drill into it with nuclear bombs, right?
No, absolutely not. Exploding an asteroid is a terrible idea because then instead of one giant bullet heading for Earth, you just have a massive shotgun blast of radioactive debris heading for Earth.
Not ideal.
No. The actual strategy relies on orbital mechanics. And in 2022, humanity proved we could do it with a mission called DART.
The double asteroid redirection test. I absolutely love this concept. We essentially played cosmic billiards. We aren't trying to blow it up, we just crash a spacecraft into a rock to slightly nudge it off course.
That's the basic premise. But how they measured the success is the truly ingenious part.
Oh, because it's hard to tell if you moved it.
Right. If you just crash a probe into a solitary asteroid orbiting the sun, a tiny shift in its massive multi-year orbit would take a very, very long time to measure from Earth. So NASA targeted a binary asteroid system.
Okay, so there was a large asteroid called Didymos.
Yes, and orbiting around it was a smaller moonlet called Dimorphos.
So basically a rock orbiting a bigger rock.
Precisely. NASA aimed a refrigerator-sized spacecraft, traveling at 13,000 miles per hour, and slammed it dead center into the smaller moonlet.
Wow.
And because Dimorphos was orbiting Didymos area 11 hours, astronomers on Earth could watch the moonlet pass in front of the larger asteroid, creating a mini-eclipse.
Oh, that's brilliant. By measuring the timing of those eclipses before and after the crash, they could immediately see if the moonlet's orbit had sped up or slowed down.
Exactly.
So they basically just checked its lap time. And it worked, didn't it?
It did. The kinetic impact physically shortened the moonlet's orbit by over 30 minutes. It transferred enough momentum to permanently alter a celestial body's path.
That is wild.
And if you scale that up, if you hit an Earth-bound asteroid early enough, a microscopic change in its trajectory will magnify over millions of miles of travel, causing it to miss the Earth entirely.
It is a profound milestone. For the very first time in our planet's history, a species possesses the mechanical capability to engineer its own survival against a cosmic impact. We actually learned how to move the scraps around the yard.
We did. It's an incredible achievement.
But you know, while we're figuring out how to dodge the big rocks, Earth is actually constantly plowing through the tiny ones, right? And instead of causing a tragedy, they give us one of the most beautiful light shows in nature.
Yes. On a daily basis, the Earth's atmosphere sweeps up tons of cosmic dust and small pebbles. When you look up and see a shooting star, you are witnessing the violent end of a tiny piece of space debris plunging into the atmosphere at tens of thousands of miles an hour.
And it's not just friction that makes them glow, right? It's something called ram pressure.
That's right.
Because the rock is moving so fast that it violently compresses the air right in front of it. And when you compress gas that rapidly, it heats up to thousands of degrees. That superheated air is what scorches the rock and creates the glowing streak of a meteor.
Exactly.
Actually, terminology time, we should probably clear up the confusing naming convention of these rocks because it always trips people up.
Good idea.
So, a meteoroid is a small chunk of rock or dust drifting in space.
Right.
But a meteor is when that chunk hits the atmosphere and burns up in a streak of light, the shooting star. And a meteorite is the surviving rock if a piece is big enough to actually land on the ground. So it's literally just a real estate issue. Space, sky, or in your hand, location, location, location dictates the name.
That is the perfect way to remember it. And the coolest part of meteors is how they connect back to the comets we talked about earlier.
Oh, right, the meteor showers.
Yes. This is a beautiful piece of cosmic recycling. When a comet swings near the sun and sublimates, remember how we said solar wind and radiation blow the dust and gas away?
Yeah, the two tails.
Well, the heavier dust particles tend to linger along the comet's orbital path. The comet essentially litters its entire elliptical lane with a tube of dirty debris.
And because the solar system is basically a giant, predictable clockwork, sometimes Earth's orbit directly intersects with one of those debris tubes.
Exactly. When you hear about an annual meteor shower, like the Perseids in August or the Leonids in November, you are looking at the calendar of Earth's highway intersections. Every year, at the exact same time, Earth drives headlong into a dusty trail left behind by a specific comet's previous flyby.
So we are basically driving a car through a swarm of cosmic gnats. Those dozens of shooting stars lighting up the sky are quite literally the crumbs of an ancient comet burning up in our air.
That's a great visual.
And the parent comet might be totally invisible to us, drifting back out in the deep freeze of the Oort cloud, but its ghostly footprint is still putting on a show for us here on Earth.
It perfectly illustrates how dynamic the debris field is. But, as we wrap up this deep dive, we really have to look at the most profound mystery these scraps hold.
Right, because it's not just about how they light up our sky, or even how they threaten our future. It's about the active role they played at the very beginning of Earth's history.
Yes, because 4 billion years ago, during a period called the Late Heavy Bombardment, the solar system was incredibly chaotic. The young Earth was getting constantly hammered by comets and asteroids.
And for a long time, the scientific consensus was that icy comets were the delivery vehicles that brought water to a dry, molten Earth, slowly filling our oceans. Which, logically, makes a lot of sense.
It made perfect sense. Comets are full of ice, Earth needed water. But recent advancements in studying these offcuts have complicated that picture in a really fascinating way.
Because we aren't just looking at them through telescopes anymore.
Yeah, we've gone to them. Missions like OSIRIS-REx and Hayabusa 2 have flown alongside them, landed on them, and physically scooped up pristine samples from near-Earth asteroids, bringing them back to labs.
And when scientists analyzed the chemical fingerprints of the water locked inside those rocky asteroids, they found a startling match, right? It comes down to isotopes, the ratio of heavy water to normal water.
Yes, water is H2O, but sometimes a hydrogen atom has an extra neutron, making it heavy deuterium. The ratio of deuterium to normal hydrogen acts like a barcode.
Okay.
And when scientists measured the barcode of the ice in comets, it didn't match the water in Earth's oceans. But when they measured the water locked inside rocky, carbon-rich asteroids.
The barcode was a near-perfect match.
Exactly.
So the dry, rocky asteroids from closer to home were actually the ones smuggling the water in.
It appears so. And not just water. Those pristine asteroid samples were found to contain complex organic molecules like amino acids.
The literal carbon-based building blocks of biology.
Yes. The implications are staggering. During the brutal violence of the early solar system, these ancient scraps were relentlessly colliding with our planet. But in doing so, they may have seeded the barren crust with the exact chemical cocktail required for life to begin.
It is the ultimate poetic irony. The exact same type of space rocks that darkened the skies, triggered global winters, and ended the 150 million year reign of the dinosaurs.
Might have also delivered the raw ingredients that made human life possible in the first place.
They are the destroyers and the creators of worlds. Not bad for a pile of leftover offcuts in the cosmic yard.
They really are the alpha and the omega of our planetary story. Understanding them isn't just about protecting our future from an impact. It's about untangling the mystery of our own genesis.
I couldn't have said it better myself. So here's a final provocative thought for you to mull over. The next time you walk into your kitchen and pour yourself a glass of water from the tap, or hey, even just look down at the skin on your own hands, think about where those molecules might have originally come from.
It's a crazy thought.
Before they were part of you, before they were even part of the Earth, they might have spent billions of years drifting in the chaotic, freezing edges of the solar system. You might just be built out of the very same space scraps we've been talking about today. Until next time on The Deep Dive, keep looking up.